In this slidecast, we'll talk about recursive definitions of mathematical formulas. Mathematicians often use recursive definitions for formulas that lead naturally to recursive algorithms. Examples are factorials, powers, and GCD. The factorial of n, or n factorial is how it's written, it's defined as follows. The factorial of 0 is equal to 1, and the factorial of n is equal to n times n minus 1 factorial for n greater than 0. So the base case is for n is equal to 0, and the second formula is a recursive definition. So the recursive definition can be expressed by the following algorithm. So here's our pseudocode for n factorial. If n equals 0, n factorial is 1, else n factorial is equal to n times n minus 1 factorial. And the last step can be implemented as in this fashion in C++. We'll have a function called factorial, and here's a trace of the call to the factorial of 4. So the factorial of 4 is equal to 4 times the factorial of 3. So if we evaluate this recursive call, its result is the 3 times the factorial of 2, and so forth until we finally get the factorial of 0, our base case, that's equal to 1. So then we start unwinding the recursion. If we return 1 times 1, which equals to 1. So 1 is the result of the factorial of 1. If we return 2 times 1, we get 2. 3 times 2, we return 6. 4 times 6, we return 4 as the result of the call to factorial passing 4 as the input parameter. Here's the C++ code for our recursive function, our base case, and our recursive definition. Now if you call function factorial with a negative argument, the recursion will not terminate properly because n will never be equal to 0. So we have to make sure our recursive functions are constructed so that an appropriate stopping case is always reached. We want to avoid an infinite algorithm. So in the factorial function, we could throw an invalid argument exception if n is negative. Now if your program does not terminate properly, you'll eventually get a runtime error when there's no more memory available for your program to execute more function calls. So assuming that our activation frames continue to get pushed onto the stack, then eventually we'll run out of memory. But that could be a lot of recursive calls before that happens. Here's a recursive algorithm for calculating x to the n. So you can raise a number to a power that's greater than 0 by repeatedly multiplying that number by itself. So if we know x to the k, we can get x to the k plus 1 by multiplying x to the k by x. So the recursive definition of x to the n is x times x to the n minus 1. And the base case is x to the 0 equals 1. Now if n is negative, the recursive function is called with a minus n as the argument, and then dividing 1 by that result. So x to the n is equal to 1 divided by x to the negative n for n less than 0. Here's some pseudocode for calculating x to the n. We have our base case and 2 recursive cases depending on whether n is greater than 0 or less than 0. Here's our C++ for our function called power that takes x as the number being raised to a power, that's our base, and n as our exponent. And we'll return x raised to the power n. And here's our C++ code for doing that. We can also solve GCD using recursion. So the greatest common divisor of 2 numbers is the largest integer that divides both of them. So the GCD of 20 and 15 is 5. The GCD of 36 and 24 is 12. The GCD of 38, 18 is 2. The GCD of 17 and 97 is 1. Now, given two positive integers m and n, with m greater than n, then if n is a divisor of m, then the GCD of m and n is equal to n. Otherwise, the GCD of m and n is equal to the GCD of n and m mod n. Okay, this equivalence was determined by Euclid thousands of years ago. But so the GCD of m and n is equal to the GCD of n and m mod n. And remember, our mod operator is the remainder that's left over after dividing m by n. So here's some pseudocode. If n is the divisor of m, the result is n. Otherwise, the definition that we just saw. So how can we verify that an algorithm is correct? So first, we have to think about whether the base case is correct. So the base case is n is a divisor of m. So the solution is n, meaning n is the greatest common divisor, which is correct. Now, does recursion make progress to a base case? So both arguments in each recursive call are smaller than in the previous call. And the new second argument is always smaller than the new first argument. So m mod n must be less than n. So eventually a divisor will be found, or the second argument will become 1, which is a base case because it divides every integer. Here's our recursive GCD function in C++, where we'll take m and n as parameters. If the m mod n is equal to 0, then that means n evenly divides m, so n is the GCD. Otherwise, if m is less than n, then we return the GCD of n and m. So here's where we just simply switch the arguments and make a recursive call. Or otherwise, we use this equivalence using the mod operator from Euclid. Now, recursion versus iteration. There are similarities between the two. In iteration, a loop repetition condition determines whether to repeat the loop or to exit from the loop. And in recursion, the condition usually tests for a base case. You can always write an iterative solution to a problem that is solvable by recursion. The recursive algorithm may be simpler than an iterative algorithm, and thus easier to write, code, debug, and read. Most of the recursive algorithms and functions you have seen so far are examples of tail recursion or last line recursion. So these algorithms have a single recursive call, and it's the last line of the function, such as in the factorial function. So it's a straightforward process to turn such a function into an iterative one. So here's an iterative factorial function. And we have a precondition that n is greater than or equal to 0. So here's our factorial iterative. Takes an input parameter n, sets a temporary result equal to 1, and then for k equals 1, k less than or equal to n, k plus plus, the result is equal to the result times k, and we return the result. Comparing our two factorial algorithms, the iterative function may be slightly less readable than the recursive functions, but not much. So in terms of efficiency, both are order n algorithms because the number of loop repetitions or recursive calls increases linearly with n. The iterative function is probably faster, not significantly, but because the overhead for a function call and return would be greater than the overhead for loop repetition. So the testing and incrementing of the loop control variable. So generally, if it's easier to conceptualize an algorithm using recursion, you should code it as a recursive function because the reduction in efficiency does not outweigh the advantage of readable code that's easy to debug. Now, a recursive version can require significantly more memory than an iterative version because of the need to save local variables and parameters on the stack. The next example illustrates a simple recursive solution that's very inefficient in terms of time and memory utilization. So here's some Fibonacci numbers. They're a sequence of numbers that were invented to model the growth of a rabbit colony. So the Fibonacci of 1 is equal to 1, the Fibonacci of 2 is equal to 1, And then here's a recursive definition. The Fibonacci of n is equal to the Fibonacci of n minus 1 plus the Fibonacci of n minus 2. And here's a series of our Fibonacci numbers. Fibonacci of 1 and 2, and then the Fibonacci of 3 is 2, Fibonacci of 4 is 3, and so forth. So here's a C++ implementation of Fibonacci. The Fibonacci of some input parameter n, if n is less than or equal to 2, then we return a 1. Otherwise, here's this recursive definition where we'd make 2 recursive calls to Fibonacci and then add together the results. So here's a picture that shows the trace. If we have the Fibonacci of 5, then that would be, we would add together Fibonacci of 4 plus the Fibonacci of 3. And the Fibonacci of 4 is going to be the Fibonacci of 3 plus a Fibonacci of 2, etc. I mean, this is inefficient, partly because we're recomputing answers more than once. Notice here's a Fibonacci 3, and here's a Fibonacci of 3. Here's Fibonacci 2 is repeated 3 times. So there's lots of repetition. So because of the redundant function calls, the time required to calculate Fibonacci increases exponentially with n. So if n is equal to 100, there'd be approximately 2 to the 100th activation frames. In base 10, that's 10 to the 30th. So if you could process 1,000,000 activation frames per second, it would take you 10 to the 24th seconds, which is about 3 times 10 to the 16th years. So here's a recursive algorithm that for any, as n grows into some reasonable size, it'll be too expensive to compute. So here's an order n recursive Fibonacci function. So here the function takes 3 parameters. Fib current is the current Fibonacci number, fib previous is the previous Fibonacci number, and then n is the count of Fibonacci numbers left to calculate. And we'll return the value of the Fibonacci number calculated so far. So here, let's look at the actual definition. The base case, if n equals 1, then we return fib current. Otherwise, we return the result of a recursive call where we pass in fib current plus fib previous. Fib current is the second parameter, and n minus 1. So in order to start the function executing, we have to provide a non-recursive wrapper function. So Fibonacci start, passing in int of n, we return the Fibonacci with the parameters 1, 0, and n. And this initializes our current and previous correctly. So let's trace this function. If we start with Fibonacci start with a 5, then we'll turn around and we'll call our Fibo with current, previous, and n as our parameters. And the result of that, we'll continue to call Fibo with 1, 1, 4, so you can keep seeing the recursive calls. The final parameter n continues to be reduced until eventually n equals 1, and at that point we just return current. So the value 5 is returned here. So this is very efficient. We've reduced our exponential algorithm to an algorithm of order n, where n is reduced by 1 every time, so eventually when n finally equals 1, the answer will be in the first parameter current, and we'll simply return that value. And that value is just returned as we unwind our recursive calls. And that brings us to the end of this slidecast.